So I would like to welcome everybody to the public presentation of Prince Tiwary, who is a doctoral candidate in our research group and has his PhD exam this afternoon. And the public presentation is part of the doctoral examination since a few years. So Prince got his bachelor and master, actually an integrated master in India, the National Institute of Science and Education, Science, Education and Research in Bhubaneswar in India. And already at that time, he actually spent quite a bit of time doing research in Europe, various institutions. And then he joined our group in 2016 and has been working on a very difficult experimental project that involves both trapped ion mass spectrometry and fluorescence spectroscopy on these trapped ions. Not only that, he also did spectroscopy of ions as they desolvate in an electrospray plume. But I think rather than telling the whole story myself, I think I should let you tell the story, and just to be sure that we don't have a lot of disturbance, the audience should mute themselves, and also probably in the interest of bandwidth, we don't really need the cameras on. So Prince, the screen is yours.
Thank you, Renato, and welcome everyone. Thank you for joining me for this public PhD presentation. I will quickly share my screen. Okay. So today I will be talking about my doctoral work, which is focused on development of new instruments and techniques for laser spectroscopy of gaseous biomolecules. In the next 30 minutes, I will talk you through our motivation, why we do what we do. I will guide you through the instrument development process, and we will see if the instrument is good enough for studying molecules that we want to study. And in two applications of our instruments, I will show you the development of a ultra-short molecular ruler in the gas phase to measure distances within biomolecules. And we'll also see the detection of gaseous protein ions under ambient conditions. So let's get started. Biomolecules are very important for living organisms. They enable a variety of biological functions, and unfavorable changes in their structure can cause key disease or even death. So it is important that we study their structure, and then we can also model their functionality. Traditionally, it is done in solution phase, but the heterogeneities in the structure and complexities of the solution phase sometimes make it difficult. An alternative is to study them in isolated form in the gas phase. It also offers different advantages. The first is the emergence of native mass spectrometry. With native mass spectrometry, it is now possible to study large gaseous biomolecules and their assemblies in the gas phase and extract their stoichiometry and other informations. However, it is still a big question that if those biomolecules in the gas phase preserve their native structures or not. If we can answer these questions, then the adaptability of native MS in biosciences will increase. Also, the protein folding is defined by the intrinsic conformational and dynamic preferences of a biomolecule and its interaction with the solvent. And often the intrinsic properties of the biomolecule are not properly understood. If we study them in an isolated form in gas phase, then we can have a baseline to which we can compare the solvent effects as well. And also in the gas phase, we do not have any techniques like NMR or X-ray, which can give us very high resolution structural information. So we have to rely on molecular dynamics simulations. But for molecular dynamics simulations, we need structural constraints to guide those simulations and derive the structure. Studies in gas phase can give us those constraints so that we can have better molecular dynamics simulations. As I told you, that mass spectrometry is a very powerful tool to study gaseous ions. It gives us accurate mass information, which helps us to identify protein in a heterogeneous sample. And we can also detect any modifications in it or any ligands bound to it. There have been various techniques which have been coupled to mass spectrometry, like collision-induced dissociation, ion mobility spectrometry, and HD exchange, which gives us information about structure of the biomolecules in gas phase. But those information, although are good, are not sufficiently enough to characterize the biomolecules in entirety. A very powerful technique in biosciences to study biological structures and function is also fluorescence. Let me tell you briefly about it. There are different electronic levels within a molecule. And when we excite the molecule with light of appropriate energy, then they get excited to higher energy states. And after coming to the ground vibrational state of the first excited state, they can come down to their ground state by different methods. One of it is emission of photon, and this is called fluorescence. We generally see it in these in our daily lives, in these compact fluorescent light bulbs, where when we supply electricity, the mercury vapor inside gives UV light, which excites the phosphor coating, giving fluorescence light. In biosciences, the fluorescence-based techniques are used as structural probes, molecular rulers, and also as sensitive probes of environment. Combining the sensitivity of mass spectrometry with selectivity of mass spectrometry with sensitivity of fluorescence can give promising results to understand the structure of biomolecules. Recently, nanometer scale structural information from a gaseous protein was extracted using Foster resonance energy transfer in the gas phase. Also, the small structural level fluctuations were also measured using dynamic contact quenching. And non-covalent probes and intrinsic protein fluorescence are also promising tools which can give us more information about gaseous proteins. So with this motivation, I started my PhD and we started to develop some instruments. One of the first projects I worked on was to develop an FTICR mass spectrometer to enable fluorescence spectroscopy on trapped ions. On this project, I worked with the then postdoc in our team, Martin Zar, and we first of all got this mass spectrometer working because it was not working before. And then we had an electrospray source which generated gaseous ions. And the gaseous ions were transported to the ion trap using the ion optics. And while they were trapped in the ICR cell, they were excited with laser light and the fluorescence was collected from them. And we were successful in developing this instrument, and we could also acquire very nice fluorescence signal from this rhodamine dye within 10 minutes, and the signal to noise was also very nice. But when we started the first measurements on proteins in 2018, there was a critical electronics failure, and we had to stop working with it. Since then, our group has invested a lot in the electronics and data systems for the FTICR, and another new postdoc in our lab, Edward, has been able to bring FTICR back to life in 2020. And soon we are expecting that we will get fluorescence signal from FTICR again. However, when we were working with the FTICR, Martin and I realized that the fluorescence signal was not very high, and we had to really fight for each photon that we wanted to detect. And the reason specific to the FTICR for this was that the ion cloud was elongated. It was cigar-shaped. And since it is not a point source, when we collect that fluorescence light and focus it on our detector, it can be a slit of the spectrograph or an optical fiber, we lose a lot of light. And that's why the signal is not very high. And in general, in gas phase fluorescence spectroscopy, we have to fight with low fluorescent signal. And there are many reasons for it. The most prominent is the low ion density. The ion density in gas phase is of the order of femtomolar. And to give you an idea of how low femtomolar is, it is equivalent to adding just 2 grams of rhodamine dye in entire Lake Zurich, which has a volume of 4 trillion liters. So very low. So apart from this low ion density, we can also not use high laser power because the ions tend to photodissociate easily in the gas phase in absence of any solvent molecule to where they can effectively dissipate heat. And also, since the ions are trapped inside an ion trap inside a mass spectrometer, the amount of light we can collect from them is not so high. All of these result in very low signal, and then it results in that you have to do experiments for longer and you are not sensitive to low brightness dyes. So we wanted to tackle this, and to get high fluorescence signals, we wanted to modify, we acquired a quadrupole ion trap, and we wanted to modify it so that we can have high fluorescence signal. On the right side, you can see schematic of the quadrupole ion trap. We generate ions using an electrospray source and transport it to the with ion optics to the ion trap. Inside the ion trap, the ions can be trapped. They can be mass selected and also mass analyzed, and further can be detected by the ion detection system. The advantage we have with the QIT for high fluorescence collection is that the geometry of the ion trap is favorable for us. The inner diameter of the ring electrode is just 7 millimeters, and this allows that we can place our fluorescence collection lens very close to the ion cloud, and thus we have more collection solid angle for fluorescence. Also, the ion cloud shape is elongated spheroid, which means that the optics is simpler and we do not lose a lot of photons in transmission. What we want to do in this setup is to modify it such that we can excite the trapped ions with laser beam and collect the fluorescence light from it. And to go about this modification, we opened up the mass spectrometer. We took this top lid out, which housed the ion optics and the ion trap, and our machine shop accurately measured it and replicated the top lid and the ring electrode. And the ring electrode is where at the center of which the ions are trapped. And here I am showing you the cross section of the ring electrode. The ions are trapped here. And we want to place our lens here. And now we have to decide what size of hole do we drill to put the lens in. Ideally, we would like to have as large hole as possible because that gives us a lot of photons, a lot of area for fluorescence collection. But since the ions are trapped in the electrodynamic field generated by the ring electrode, drilling a large hole might influence the performance of the mass spectrometer. So we did some simulations and calculations, and we found that drilling a 5 millimeter hole would be safe enough, and it would also give us fluorescence collection efficiency of around 2.3%. So more details of this instrument modification you can find in this publication, but I will summarize it like this. We generate ions using nano electrospray ionization. We trap them and mass select them, and we excite them with a laser light. And the collected fluorescence can be used for a variety of experiments. We can perform excitation and emission spectroscopy from them. We can image the ion cloud, and we can also do fluorescence decay experiments, which can give us the fluorescence lifetime. And the key feature of our newly developed system is that we have a very high fluorescence signal. And it is because of two factors. The first one, I already told you that we have high fluorescence collection efficiency of 2.3%. And also the helium buffer gas pressure inside the ion trap is around 2.1 millitorr. And this increased pressure allows us to excite, decreases the photodissociation and thus increases the fluorescence signal. And now I can show you the different spectra that we could acquire from our newly developed instrument. And you can see that we can acquire fluorescence in a range of wavelength, and we can also acquire it from a variety of analytes like rhodamine dyes, ubiquitin protein labeled with rhodamine dye, and also a lipid which was labeled with another dye. And we could also acquire an excitation spectrum. So now that we have developed our instrument, we would obviously like to compare it with the other ones. Let's compare it locally first. Compared to the FTICR, we can see that in less time, we have better signal to noise. And if we take into account other factors which influence the signal intensity, we can see that it is nearly 40 times better compared to the FTICR. And what this means is that the experiments we can that would take 1 hour on the FTICR can be it can be done on the QIT on just 1.5 minutes. So it saves us a lot of time. Compared to the other quadrupole ion traps, which have been modified for fluorescence collection, we are nearly 10 times better. We are second only to the cylindrical ion trap, but the quadrupole ion trap we have developed gives us advantage for studying gaseous biomolecules, as we can perform lifetime experiments, which helps us interpret complex fluorescence signals. Now, I would also like to add a remark here that the FTICR and QIT both have their advantages and disadvantages. QIT gives us very high fluorescence collection efficiency. It saves us a lot of experimental time and makes us sensitive to low quantum yield dyes. But the mass range of QIT is up to 2000 Daltons and can be extended to 3000 Daltons. So we can study small dyes, peptides, and up to small proteins with QIT. However, with FTICR, even though the signal intensity is low, its mass accuracy is very high, and the mass range is also till 5,000 daltons. So we can study large proteins with FTICR. So in our lab in total, we have all the facility, we have covered the range. We can do from low quantum yield to high quantum yield with QIT, and to small proteins, small dyes with QIT, to large proteins with the FTICR. So let's focus on the QIT, and let's put it to test and see if we can, if it performs the way its numbers are. So to test it, we wanted to study fluorescence from a thioflavin T, which is not so bright dye. It has a quantum yield of just 0.01. Compare it to rhodamine, whose fluorescence I just showed you. Rhodamine has quantum yield of 1. What it means is that for every 100 photon that you excite rhodamine dye with, you get 100 fluorescence photons. But for every 100 photons that you excite thioflavin T dye with, you only get 1 fluorescence photon. So thioflavin T dye is nearly 100 times less bright compared to rhodamine dye. But it is a very popular dye in condensed phase, as it acts as a non-covalent probe for biomolecules. And if we understand its photophysics well, we can also use it in the gas phase as a non-covalent probe. Recently, its gas phase fluorescence spectrum was acquired. And here I would also like to point that the key challenge, I would also like to remind the key challenge in the gas phase fluorescence spectroscopy, which is low signal. And as I already told you that in gas phase fluorescence spectroscopy, the signal is low. And the quantum yield dye is again a very low quantum yield dye. So it is not very bright. So it was extremely difficult, but the authors were very skillful and they could acquire the fluorescence spectrum. However, the signal to noise was not very high, and it was difficult to identify where the fluorescence emission maximum is. To do this, smoothing techniques were used, and it looked like the maximum was around 500 nanometers. They also performed this experiment in different conditions, and they took thioflavin T dication. They encapsulated it in cyclodextrin and also measured its fluorescence in solution. And what they concluded was that the emission maximum of thioflavin T dye is independent of the medium. It resonated well with the conclusions from the solution phase experiments, where they found that the polarity of the solvent doesn't influence the emission maximum of thioflavin T dye. However, I was not very convinced by this conclusion, and I will tell you why. So you can see here towards the right side that there are different electronic levels inside in a molecule, and the difference between them defines where the emission maximum will be. What happens when there are solvent molecules around the dye is that the solvent relaxes the energy levels of the dye, and it is higher in the gas phase if the excited state is more polar. In the case of thioflavin T dye, there is free rotation around the benzothiazole, this single bond for this benzothiazole group and the benzene ring. And this free rotation stops the solvent molecules from getting into equilibrium with the dye. So there is a partial non-equilibrium. And this results in the decreased relaxation by the solvent. And since they are in partial non-equilibrium, then that's why the solvent doesn't influence the relaxation that much. And in turn, we get low dependence of fluorescence emission maximum on the in fluorescence. However, even if we go from here, if we compare the partially relaxed condition and the energy difference, and in the gas phase, it is still higher. And when the molecule goes from the solution phase to gas phase, we will expect an increase in the energy difference. And this would mean that the fluorescence spectrum shifts towards lower wavelength sides, and we see a blue shift. So we measured the fluorescence spectrum of thioflavin T dye with our instrument, and we saw that we do see a decrease in fluorescence. We do see a blue shift, and it is around, the maximum is around 478 nanometers. It matched with the fluorescence measurements of thioflavin T dye in amyloid fibrils, where the maximum is around 478 nanometers. And this insight we could only get because we could acquire the fluorescence spectrum with high signal to noise. And thus our instrument is not only useful to decrease the experimental time, but also gives us insight into low quantum yield dyes. With this, I would like to move towards the next topic, which is development of an ultra-short molecular ruler. So generally in the gas phase, in solution phase, FRET, phosphoresonance energy transfer, is used for as a molecular ruler. What it tells us about conformational changes by allowing us to monitor the fluorescence signal. And for FRET experiments, we label a biomolecule with a donor dye and an acceptor dye, such that the emission of the donor overlaps with the absorption of the acceptor. And whenever we excite the donor, there is a non-radiative energy transfer from donor to acceptor, and we see fluorescence from acceptor. This process is highly distance dependent, in fact, inverse sixth power dependent on the distance. And so when the donor and acceptor are closer, we see high fluorescence FRET efficiency, and when they are further apart, we see low FRET efficiency. And this can be monitored by either looking at the intensity of fluorescence from donor acceptor or just monitoring the fluorescence decay of the donor. However, there are certain disadvantages with conventional FRET. Dual labeling of the dye is necessary because we want to put donor and acceptor, and this is often a complicated and long process. And generally, it measures distances in the range of 20 and 80 angstroms, which is towards the higher end of the distances we generally measure in the gas phase. We had a condition many times in our lab that we wanted to measure FRET within a biomolecular system, and the donor and acceptor ended up being so close that we got 100% FRET efficiency, getting no information from them. And it is also difficult to validate the results since we would need to label the dyes again, and which is again long and process. An alternative of traditional FRET has emerged, which is called transition metal ion FRET, where the acceptor is replaced by a transition metal cation, which non-covalently bonds with a histidine placed in the peptide or protein chain. And in this case, only a single dye label is required. It measures a distance between 5 to 20 angstroms, which is more relevant for our gas phase measurements. And it is also very easy to check the results, as we only have to replace this transition metal cation. So we designed a model system of helical peptide where we had a cysteine linked, use a linker, and then we had a dye here. Selection of dye is very critical here because not all fluorescent dyes are fluorescent in gas phase. And also we want a bright dye such that because the intensity will decrease because copper will act as a dark quencher. And its fluorescence emission should overlap with the absorption of copper. So we selected rhodamine 110, which satisfied this criteria. And we can also see that the fluorescence emission from the dye here and overlaps with the absorption of copper shown by this hatched triangle. To check if this system indeed goes transition metal FRET, we first checked it in the solution phase. And you can see here that we titrated the models with the dye label to peptide with copper 2+. And there was a decrease in intensity with increasing intensity of increasing concentration of copper. This confirmed that our system can undergo transition metal FRET in solution. Now we had to check it in the gas phase. To study it in the gas phase, we electrospored it, we acquired its mass spectrum, and you can see that we see different charge states of the bare dye and also its complex with copper in different charge states. And then we mass selected the 3+ charge state of the bare peptide labeled with dye, and we acquired a fluorescence decay, fitted it to get a lifetime, and the lifetime was around 6.3 nanoseconds. And next to it, we took its complex, mass selected it, and acquired its lifetime. And you can see that there is a clear decrease in the lifetime, which shows that there might be transition metal FRET, but we would like to be skeptic. It can be some other process like some influence of charge as well. So we wanted to check the key criteria of transition metal FRET. And what is the key criteria of a FRET? It is the distance dependence. So we designed model systems which had the donor, which was labeled to the cysteine, and acceptor, which binded to the histidine at different distances. Here they are closest and here they are furthest, and acquired first fluorescence spectrum from just the bare dye labeled to peptide in 3+ charge state, and there was not a lot of difference in their lifetime, and then their lifetime in when copper was bound to it. To show it simply, I will just show it in one graph. And you can see here that when bare peptide was used, we did not see any change in the lifetime. But when copper was bound to it, we see that there is a change in lifetime. And it is maximum in case when the donor and acceptor are closest, and least when donor and acceptor are furthest. And if we compute the FRET efficiency using this formula, using this data, we can see that the FRET efficiency is highest when the donor and acceptor are closest and least when they are further apart. Now, this monotonic decrease in FRET efficiency with increasing donor acceptor distance confirms that we can get transition metal FRET in the gas phase. Now we can use this formula, which is inverse dependence, power dependence of efficiency with the donor acceptor distance. We can and have some assumptions on the R0 gas Foster distance. We can calculate the distance between donor and acceptor, and it came out to be 11 angstrom, 14 angstrom, and 15 angstrom. So we have demonstrated that the transition metal FRET can be done in the gas phase, and we have also obtained some estimate of the distances which match with our expectations of the distances within the gas phase. Now we can move towards the last part of our talk, which is about detection of gaseous protein ions under ambient conditions. Why would we like to study gaseous protein ions under ambient conditions? So the ions are, for mass spectrometry analysis, generally the ions are generated using an electrospray source where we have a sample where, to which we apply a high voltage, and when there is a counter electrode, then it electrosprays, and first it forms charged droplets, and they undergo repeated cycles of droplet fission and solvent evaporation, leading to the formation of gaseous ions. However, we have seen, and many other groups have also shown, that the mass spectrometer had some influence on the structure of the proteins, and also its structure evolves in the course of electrospray. And if we study them in the electrospray, it also gives us a chance to understand the electrospray ionization mechanisms, which are in general difficult to understand. So we designed an experimental setup around it so that we can excite the electrospray plume at different distances and collect fluorescence light from it. And since fluorescence is a sensitive probe to the microenvironment, we expect to see changes when it goes from solution to gas phase. But to study proteins in ambient conditions, first we need to desolvate them. And there have been no reports of this observation of fluorescence-based observation of desolvated proteins under ambient conditions. Earlier, it was tried with 50 micrometer inner diameter tip, but that they generate larger droplets which are difficult to desolvate within the time span we can observe. And thus we decided to use 5 micrometer inner diameter capillaries, which generate smaller droplets. But when we sprayed a small dirhodamine B from water, we did not see a blue shift. And since we did not see a blue shift, we expect that there was no gaseous ions present. However, we could see gaseous ions, a blue shift when methanol was used, which is a more volatile solvent. But this shows that our setup can detect gaseous ions, but just from water, they are not dissolvating fast enough. So to accelerate this dissolution process, we wanted to generate smaller droplets which dissolvate faster. So we decided to use tips which were less than 1 micrometer in inner diameter, and we electrosprayed rhodamine 6G from aqueous solutions. And now you can see that within 4 millimeters, we see a blue shifted peak, which means that it has dissolvated. And since we can now dissolvate gaseous protein, the dye, we also want to try it with the proteins. And we tried it with ubiquitin and epomyoglobin. We labeled it with carboxyrhodamine 6G and acquired its fluorescence from different parts in the plume. And you can see that at the maximum distance we could acquire, the peaks look blue shifted, but are they really from dissolvated proteins? To find if they are from dissolvated proteins, we acquired the spectrum of these labeled proteins in the true gas phase in the ion trap. And we tried to fit the spectra that we acquired in the ion trap and the spectrum that we had acquired in the solution to these blue shifted peaks, and extracted the contribution of solvated and desolvated species. And after fitting the spectrum, we could see that more than 90% of the species present in the plume are desolvated. And this we could observe because we used a smaller inner diameter tip, which formed smaller droplets and which led to faster dissolution. So now it is possible to generate gaseous protein ions under ambient conditions. And this also opens, and now you can ask that if we do not have chemical specificity, we are studying everything. For that, our team members, Yunus and Edward, are working on coupling differential mobility analyzer, which can allow us to select a certain chemical population in ambient conditions. So with this, I would like to conclude my talk. I showed you the motivation to study gaseous biomolecular ions with fluorescence spectroscopy. I guided you through the instrument development process. We saw that our instrument is good enough to study even low quantum yield dyes like thioflavin T. And I showed you the first evidence of ultra-short molecular ruler in the form of transition metal fret in the gas phase, and also the first detection of fluorescence-based detection of gaseous protein ions under ambient conditions. I would leave you with these takeaway messages. The first is that we have developed instruments in our lab which allow laser-induced fluorescence studies in different media. In solution phase, in the plume, in early stages after dissolution, and in vacuum when they are mass selected in an ion trap. And we can do these experiments with high fluorescence collection efficiency of 2%. And we can also perform diverse experiments like spectroscopy and lifetime. And I showed you two applications which were with low quantum yield dyes and observation of gaseous protein ions under ambient conditions. We also developed FTICR, which gave us high mass range and longer time frame for observation of biomolecules. And I showed you the ultra-short molecular ruler in the gas phase. With this, I would like to conclude the talk and thank several people. First of all, my supervisor, Professor Renato Zanobi, for giving me this wonderful opportunity to work on these exciting projects. It has been fantastic. And my teammates, mostly Martin Zar and Yunus, for working with me on the gas phase fluorescence projects. It has been challenging, but it has also been fun working with you. And also Edward, Guido, and Mario for cooperations during the time in the lab. I would specifically like to thank the people from chemistry workshop, Christoph, Christian, and Marco, who designed and made all the instruments that the instrumental components that you saw during the talk. And they designed it with high accuracy. It was fantastic. And Heinz for helping us with electronics, members of Zanobi group for fantastic environment in the lab, and also family and friends for moral support. And I would also like to thank you for your time, and I'm open to take questions.
Yeah, thank you very much, Prince. Nice presentation. So the talk is open for discussion. I personally won't ask many questions. I'll save mine for the afternoon when you have your PhD exam. But whoever wants to ask a question, I would suggest also show the camera and quickly identify yourself.
Oh, sure.
Hello, Prince. Oh, I guess there's a lot of mics. Maybe also turn off the volume. Sorry. So I wanted to ask about the, that's weird. I don't know. Maybe also the volume. Okay, sorry. So I wanted to ask, when you're measuring the fret in the gas phase in the trap, is the peptide is still kind of dynamic and you're measuring like the average distance, or the peptide itself not dynamic and it's kind of frozen, that you actually see the distances that you see, like those 11 angstroms, 14 angstroms, and 15 angstroms? I'm just curious about, like, is that the actual distances, or is that the average distances of kind of like the dynamic of the protein?
Sure. I think the distances that we measure are going to be some sort of an average, because the molecules are anyway going to be dynamic. But I think that the distribution will not be very high. And also, to understand their behavior better in the gas phase, we have collaborated with for molecular dynamic simulations, and they can give us more insight. But I think we have some sort of an average.
So just to like a little bit more.
Yeah, sure.
So for example, in the ESI process, and when we have the dissolution, right, the molecules or the proteins, for example, they kind of get into this a bit of a frozen state, and then they go into the gas phase, at least from what I'm understanding.
Yeah.
And in the gas phase, so they do not retain this kind of frozen state. They're still kind of a dynamic because of the bonds inside rather than the environment around. Am I understanding it correctly?
Your understanding is right. So for large proteins, you have large internal baths, so they are kinetically trapped and they do not move that much. But for small peptides, they can still move enough. And what we were studying was a small peptide, so it has, I think it can move.
Just to add, it was a very fantastic talk, especially that you persevered through so many problems and did not give up and did so much amazing work. Thank you.
Thank you very much.
Hi, Prince. This is Naresh.
Naresh.
Yeah, hi. Thanks for a really great talk and really great work in your PhD. So I have a very, very simple question. So can you explain why do you want to study biomolecules in gas phase again? Like, for example, proteins in gas phase?
Yes. So I showed different motivations to study biomolecules in the gas phase. And the first of it is that sometimes in the condensed phase, we have different structures present. So there is conformational heterogeneity, and it is difficult to study them with the conventional solution phase techniques. And then we also want to study their intrinsic protein interactions. And the interaction, the structure of protein is determined by its internal preferences and also its structure, its interaction with the solvent. But if we, but the internal preferences of the proteins are not clearly known. And if we understand them in an isolated environment in the gas phase, then we can obtain some sort of baseline through which we can compare our solution phase measurements and understand their influence on the protein structure. And one of the key reasons is also to find benchmark for molecular modeling. So for gas phase, we do not have techniques like X-ray or NMR, which can give us very high resolution images. So we have to depend on molecular dynamic simulations. But if we do not have constraints to guide those molecular dynamic simulations, we will not get anywhere. So from experiments like FRET, we can obtain those molecular constraints and then go towards studying studying their structure.
Dr. Himansu had a question.
Yes.
So, Prince, you have done a lot of work, and I congratulate you.
Thank you, sir.
I really liked it. I have very simple question. Though I know it's very difficult to have a fluorescence of ions. Which type of laser do you use for the fluorescence?
We have a titanium sapphire laser, which we frequency double it to obtain wavelengths in 345 to 520 nanometer range. It is also femtosecond laser, so it helps us for obtaining the lifetimes of the molecules.
Have you thought of to make the ion beams and do the fluorescence the way we do? We can have the LP or stuff for small molecules.
Yes, but in ion beams, can we have chemical specificity we can get in ion traps?
Okay.
So in ion traps, we can isolate a specific mass by charge or specific complexes. I think in ion beams, we cannot do that, right?
Okay.
Yeah, so to get more chemical specificity, we use ion traps.
So do you think you can do also the double resonance spectroscopy using one more laser?
Which spectroscope?
Double resonance.
Double resonance in our setup?
Yeah.
Yes, if we use 2 lasers, it can be done, but it is experimentally difficult to perform because the ions are inside an ion trap, which is inside a mass spectrometer, and it was already difficult to couple 1 laser to hit the ion cloud. And the size of the ion cloud is less than 1 millimeter, and the diameter of laser beam is also less than 1 millimeter. So without seeing them, it was difficult to align both of them. And if we have 3rd laser, it will even add more complexity. It can be done, but technically very complex.
Okay, thank you.
Thank you, sir.
Hi, Prince. Very nice talk. I really liked your work. I just have a question. Maybe I missed something, but does the protein keep the modifications like the glycosylation and all these things that are usually in proteins in vivo states?
There are different studies which have been done to find out. And the common perception, consensus is now that when we electrospray proteins, they are kinetically trapped, so their global structure is sort of maintained, but the side chains, they first collapse and then they form electrostatic interactions.
Okay.
Yeah. Any other questions?
Well, if there is no other questions, I would suggest to give Prince a real applause so you can quickly unmute yourself and do this. Thank you very much for the presentation.
Good timing.